today we're going to be talking about exponential functions. Here's the two basic types of exponential functions. We have exponential growth and exponential decay. In function notation, you will see the exponential function is a times b to the power of x. The a value is always going to be your initial number, just right there at the beginning. So if you're dealing with a certain type of number of bacteria, if it's growing over time, you put the starting initial bacteria to start out. If you're dealing with a word problem. The b value is called your growth or your decay rate. Okay? Now you'll notice right here, what does it say your b value is for growth? Your b value has to be greater than the number 1 if it's growing. Over here, what does it say your b value is between? Your b value is less than 1, but it has to be greater than 0. So any decimal, any fraction between 1 and 0, and you are going to be decaying. Hopefully when you buy a house someday, over time the price, how much your house is worth, will grow over time. When you buy a car, what's going to happen? Unless it's a classic, it'll decrease, right? It'll over time, all right? Now, right here it's kind of hard to see. This is a very, very, very important concept. Understand, whenever you plug in 0 into your exponential function, it will be your a value. So I'm very good at it. When you plug in 0, right here, if you plug in 0, what is any number? If I say b to the power of 0, what's that going to equal? 1. Okay? So all you're going to be left with is your a value. So that's a key concept to note as well. Whenever you plug in 0, you get your a value. Now, we're going to be talking about domain. In both of these, the domain is all real numbers. So the domain goes from negative infinity to positive infinity. But if you look at the range, what is the range? It goes from 0, but notice, it's a soft bracket. So in interval notation, if you can't see it, right there it's saying it's going from 0 to positive infinity. It's a soft bracket. It does not include. All right? Your asymptote is the x-axis. So if your asymptote is the x-axis, that means f of x is equal to 0. Or you would say y equals 0 for your asymptote. Okay? Over here, everything is pretty much the same. The only thing that's different is this is continually increasing. This is continually decreasing. All right? So one of them is increasing, one of them is decreasing. Everything else is pretty much the same except for the end behavior. So what I'd like us to do is I'd like you guys to look at problem number 1. All right? So all the way up to problem number 1. And I want you guys to make an accurate graph of this. Okay? So in problem 1, make an x and a y table. So put x and f of x. Give me an accurate drawing of this graph. All right. Right now what we're going to do is we're going to graph this. Anybody get some points to graph? 2. All right, right there. What else? 4 and an 8. Anybody get a 3 and a 4? Okay. 3, 4. This is right about here. All right, we're going to type in 2 to the power of x minus 1. This is where we're getting the numbers right here. Start a window at 0. So right here, here's some numbers that you guys can plot. We've got a 1, 1, 2, 2, 3, 4, 4, 8. We got a 0 and a half. All right. So you'll see that this graph gets closer and closer and closer to 0. And then, almost. All right, we're just Oh, the suspense. All right, here we go. All right, so here's our graph. All right, let's look at the left end behavior and the right end behavior. I want you guys to write this. I made a nice little table for you guys. This did not come on the assignment. I had to add it in. All right? Left end behavior, right end behavior, because I can. Now, when I say left end behavior, what's X always approaching on the left side? On the left side, negative infinity. No. On the right side, what's X always approaching? Positive. Okay. Now, when it says the limit of the function, as X is going this way, there is a limit. What is this never crossing but getting really, really, really close to? 0. So you say the limit of f of x is 0 on the left-hand side. But what's happening over here? It's going where? That's right. It's going to see Jesus eventually. It's going to positive infinity. Now, this is what I want you to do on your paper when I say, hey, what's the left-hand behavior? What's the right-hand behavior? Okay? Now, what I have to do now is we're going to answer some questions that are down below. Take a look at it. I'm going to go a little bit lower. Okay? Now, we'll go back and look at this. What's the domain? That was the question. What's the domain? What x values are being plotted? You say negative infinity to positive infinity. So you could say all of them. So the domain for that is from negative infinity all the way to positive infinity. In interval notation, we're not including it. That's why it's What's the range? That's right, 0 to positive infinity. Very good. 0 to positive infinity. And almost said with enthusiasm. Almost. All right, intercepts. Do we have any x-intercepts?
No.
No x-intercepts. But we do have one pesky little y-intercept. And the pesky y-intercept is when x is equal to a 0. I think we got a half for that. Is there an asymptote?
Yes.
What's the asymptote? The x-axis. So here's what I want you to do. Write down the word horizontal. We have a horizontal asymptote. And I want you to write the equation for the x-axis, which is f of x equals 0. And if you had a choice, would you say this graph is increasing or decreasing? From left to right.
Increasing.
So you say, you know what? I'm going to start. It's increasing. It's increasing from negative infinity heading towards positive infinity. What I would like you to do is I would like you guys to do the exact same thing for problem number 2. All right, so problem number 2 has this thing called E. You're like, what the heck is E? So we're going to go down here to our little notes. Going down to our notes. Notes. Look for E. All right. Now, I think we found it. A Swiss mathematician, Leonard Euler, who computed E to 23 decimal places. He figured this out right here. It's kind of hard to see, so I'll write a little bit bigger. E is equal to the limit of 1 plus 1 over x raised to the power of x as x approaches infinity. You're like, what the heck does that mean? Well, listen. If you plug in an x and you plug in a 1 right here, you get a 2. If you plug in a 10, you get 2.59. We plug in 100, you get 2.7048. As you are getting bigger and bigger and bigger and bigger, look what y becomes. It gets closer and closer to this number called Euler's number. It's an irrational number. So we'll do it in our graphing calculator right now. Okay? So let's go to our graphing calculator. All right, I'm going to go open parentheses. 1 plus 1 divided by, I'm going to type in a 1, 0, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5. Let's do a million. And I'm going to raise that to the power of a million. 1, 2, 3, 4, 5, 6. Press enter. I mean, the reason I chose a million, it's a really large number. It's not infinity, but it's a really big number. You know, maybe it's a number you'll have in your bank account someday.
Oh.
You can do it. You can do it. All right. I mean, I'd like to say I'm halfway there, but you know, I still got a ways to go. Now, in your graphing calculator, hit second and the division sign. What? Second division. Ooh, E. Let's press enter. Hey! Look what we got there. We got Euler's number. That's E. So if you wanted to, let's say you had an equation that you wanted to take a look at. Okay? Like -1 divided by 5. Hit second and division. Raise that to the power of x. And then we're going to say minus a what? Minus a 2. Okay? Now, before I hit graph, I want to look at our problems. Let's change our window right now. Okay? All right. Our x minimum, I want to put at -10. Our x maximum, +10. And the same thing with the y minimum, the y max. So go to your window, please. Go to your window setting. Type in -10, +10, make the x scale 2, make the y scale 2. So type that in before you hit graph. All right, hit graph. There we go. There's your graph. What I'd like you to do is take this graph and put it on your paper. Okay. This is the graph. Y equals -1/5 e to the power of x minus 2. This is problem number 2. Now, one thing it asks us to solve is what? The left-hand behavior and the right-hand behavior. So right now it looks like it's getting really close to this -2. Crosses through, and then it goes down like this. On the left side, x always approaches -infinity. On the right side, x approaches +infinity. You're going to need to know left-hand behavior and right-hand behavior on your 6 weeks test, so you might as well get used to it. Right. On the left side, what's the limit of this function as x is approaching -infinity? What's the limit? What's as high as it gets over here?
-1.
-2, so put -2. What's as low as it gets? On the right-hand side. So there's your left-hand behavior and your right-hand behavior. Right now I'm just going to write down the other part. You guys can fill it in. Alright, the domain is still from -infinity to +infinity. The range has changed though. The range is not at 0. What's the range? It starts where? -2 going towards -infinity. Right? Underneath range, what do we have? Intercepts? You only have one intercept, right? -11/5. Alright, so we're going to write 0, -2.2. You could put 11/5, that's fine. We got negative 2.2. That's where this is located, right there. We do have an asymptote. That's a horizontal asymptote. And this would be considered to be decreasing. It's forever decreasing. Hopefully this is not your bank account. Maybe you'll. Maybe. All right? I know. Maybe one day. All right? All right, so we call number 3. In 2000, the number of people in the United States was 281 million, blah, 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 blah. All right. The U.S. population is estimated to be growing. All right. At 0.88% annually. All right. So it says, let t be the number of years since 2000. Write a function that models the annual growth in population in the United States. So look at all of your formulas that are on your sheet, and which formula do you think best fits number 3? What do you think? N equals n subset 0, 1 plus r raised to the power of t. That's what you were talking about there, Xyla? Yeah. All right. Now, n subset 0, all right, is our initial number. Right. So here's what I want you to do. You can put y equals, you can put n equals. You can put n equals 281,421,906. That is n subset 0. 1 plus, now what is our r value? R equals rate. And rate needs to be in a decimal. But they gave it as a what? A percentage. Anytime you have X percentage and you want it to become a decimal, just divide it by 100%. Okay? So anytime you have a percentage and you want to change it to a decimal, just divide it by 100. Now, or you could say, just move the decimal over, Mr. Damood, 2 places. Well, when I move the decimal over 2 places, what happens? I have 2 zeros in front of that 88. Okay? So your rate right now for this function, your rate is actually 0.0088. So we put plus 0.0088 raised to the power of t, where t equals years. This is our function. If we wanted it to combine it into something a little bit smaller, you could write this. N equals same initial population, and you put 1.0088 to the power of t. Without having to put the plus, you just put 1.0088 to the power of t. So what I'd like you guys to do, go your graphing calculator, get y equals, let's type this function in. 281. With somebody else's paper. 421. 96. Open parentheses. 1.0088 raised to the power of, we don't have t, but we have raised to the power of s. Now that's our function. Now we have to know how are we going to use it. Predict the population in 2020 and 2030. 2020, your X value would be 20, because that's T years since what? T years since 2000. So evaluate it when X is at a 20 and when X is at a 30. So second window, we're going to start the table at 20. And we have a couple of answers here. We've got this answer right here, and we've got this answer right there. Now, obviously, the calculator can't type in all the zeros, so what does it do? It gives you e to the 8, which basically means 10 to the power of 8. So what I want you guys to do is understand that we have a 3, 3, 5, $335 million for 20 years after, so 2020, this is estimating the population to be that. And over here we have 366. So this would be 366 million. Now, to check it, it said what? It said 3.66 E 8, that basically means 3.66 times 10 to the power of 8. So if I move the decimal over, 1, 2, 3, 4, 5, 6, 7, and 8, that would work. All right? So those are your two answers for A and B. What I'd like you to do now on your own is do number 4. Find the formula and see if you guys can come up with the correct answer. By the way, it's going to tell you you're going to be dealing with something called compound interest, and you're compounding money. When you guys are doing compound interest, okay, P represents the principal amount. Like how much did you start with? Okay? How much did this person start with? 1,000. So right now, just put P equals 1,000. What's the interest rate? 4%. But 0.04. Okay. How many years? 5 years. Now the N, that represents the number of times it compounds. So since it says monthly, that number is going to be a 12. Right? So what we're going to do is we're going to plug everything in. We start out with 1,000. We're putting the monthly interest rate. By the way, if you're wondering why credit card companies make so much money, they compound their interest monthly off of whatever you owe them. Alright, so if you ever have debt with a credit card company, they're going to compound it monthly, not yearly. It's going to be every single month. They make money off every month if you have debt. So anyway, well, we're going to say 12 times 5. That becomes a 60. Right? And that will give you your amount at the very, very, very end of 5 years. It was at 4%. So we got our calculator. Right? We're going to go 1,000. Open parentheses. 1 plus. Now, you don't have to do alpha y equals enter. You can actually just do 0.04 divided by 12 and close it, that's okay. You can use it just like that. And raise it to the power of 5 times 12, which is 60. And measurement. 1,220. Oh, guess what? It's going to round up, isn't it? So if it's compounded monthly, it would be $1,221. All right, so let's say you start out with 12,000, not 1,000. You start with 12,000. Let's say you earn an interest rate of 10% over time. That's the average interest rate, 10%. And typically in IRAs, they don't compound monthly; they compound 4 times. And you just sit there and let that $12,000 just sit over time. And let's say you wait 30 years before you look at it. 30 years. You just live for 30 years. All right? What is 30 times 4?
120.
120. So you just sit there and wait 30 years. And then you look at it. What would you have at the end of 30 years? If you just sit there and live. 130,000. Wait, what if you sit there, not 30 years, but go 40 years? What would you be at?
I'd be dead.
You'd be dead? 40 years? Right, 160. What happens?
Live past
Alright, that's compound interest. Every day.